We will start this video by summarizing what we have seen so far. Before doing that, we will introduce a terminology. We will say that a linear operator L from V to V is diagonalizable if there exists a basis BV of V such that the matrix of L with respect to the basis BV is a diagonal matrix. Let us now summarize what we have seen so far in this language. We saw that if V is a vector space over R, then a linear operator L from V to V need not have an eigenvalue. And if a linear operator does not have eigenvalue, then it cannot be diagonal. Thus, if V is a vector space over R and L from V to V is an operator, then L need not be diagonalizable. However, we saw that if V is a vector space over C and L from V to V an operator, then L has an eigenvalue. Therefore, we suspected that if V is a vector space over C, then any linear operator will be diagonalizable. However, we saw later that this is not true. In other words, we saw that if V is a vector space over C and L from V to V is an operator, we saw that L need not be diagonalizable. Okay, so we see that a linear operator need not be diagonalizable, even if it is on a vector space over C. However, we do not give up. We ask the next natural question. We ask, what is the best that we can do? For instance, can we characterize linear operators that can be diagonalized? Or if we have a linear operator on a vector space over R, can we characterize linear operators that have an eigenvalue? Let us repeat. We are interested in questions like, if V is a vector space over C, can we characterize operators on V that are diagonalizable? If V is a vector space over R, can we characterize operators on V that has an eigenvalue? If V is a vector space over R, can we characterize linear operators that are diagonalizable? So these are the kind of questions that we are interested in. And in this video, we will give a partial answer to question 1. More precisely, we will give a sufficient condition. In other words, we will give a condition on L that forces L to be diagonalizable. However, not every diagonalizable operator satisfies this condition. This answer becomes even more interesting because it does not depend on whether V is a vector space over R or C. Therefore, we also have a sufficient condition under which a linear operator on a vector space over R is diagonalizable. However, this still does not completely characterize operators that are diagonalizable. Why? Because for a complete characterization, we need a necessary and sufficient condition. What is a necessary and sufficient condition? We want both ways. That means if the condition is satisfied, then L should be diagonalizable, and if L is diagonalizable, then the condition should be satisfied. We want some such condition. However, this question, finding a necessary and sufficient condition, is very difficult, and therefore we will not get into it in this course. So, after giving a partial answer to questions 1 and 3, we will address question 2 in our next video. The sufficient condition that we were discussing earlier is given by the following theorem. Let V be an n-dimensional vector space over R or C, and L a linear operator from V to V. If L has n distinct eigenvalues, then L is diagonalizable. Let us look at a proof of this theorem. Let lambda 1, lambda 2, etc. up to lambda n be distinct eigenvalues of L. Further, let Vi belonging to V be such that L of Vi is equal to lambda I Vi. In other words, Vi is an eigenvector for the eigenvalue lambda I. I forgot to mention, here we are assumed that Vi is not equal to the 0 vector. Then we had seen before that the list of vectors v1, v2, etc. up to vn is linearly independent. And as n is the dimension of V, this means that the list v1 to vn is a basis of V. Therefore, if you look at the matrix of L with respect to the basis v1, v2, v3, etc. up to vn, then we get a diagonal matrix. Now, this is easy to see, but when I made a similar claim earlier, many of you were a little confused. Therefore, let me prove that this is indeed the case. How did we determine the matrix of a linear transformation? To determine the matrix of a linear transformation, we have to fix a basis of the domain and codomain. And in this case, we are fixing the same basis, say v1, v2, v3, etc. up to vn on both the domain and the codomain. As soon as we fix the basis of V, we have an isomorphism to Rn, namely the unique map that takes the element Vi to the element of the standard basis Ei. And similarly, we have an isomorphism from the codomain to Rn. And it's the same map. Once again, it sends Vi to Ei. Recall that we called this map L1 and this map L2. Given this map, we had a map L2 composed with L composed with L1 inverse, that is from Rn to Rn. And we had defined the matrix of L with respect to the basis v1, v2, v3, etc. up to vn to be equal to the matrix of the linear transformation L2 composed with L composed with L1 inverse. So now we just need to find the matrix of L2 composed with L composed with L1 inverse. But notice that under L1 inverse, Ei gets mapped to Vi. And under L, Vi gets mapped to lambda I times Vi. And again under L2, lambda I Vi gets mapped to lambda I Ei. Therefore, we see that L2 composed with L composed with L1 inverse of EI is equal to lambda I EI. And the matrix of L2 composed with L composed with L1 inverse has as its columns L2 composed with L composed with L1 inverse of E1, L2 composed with L composed with L1 inverse of E2, and so on up to L2 composed with L composed with L1 inverse of En. But we know that L2 composed with L composed with L1 inverse of E1 is equal to lambda 1 E1. Similarly, the second column is lambda 2 E2, and so on up to the last column is lambda n En. But lambda 1 E1 is nothing but lambda 1 0 0 etc. up to 0 all the way. Lambda 2 E2 is 0 lambda 2 0 0 0 all the way, and so on. The last column, which is lambda n En, has zeros in the first n minus 1 entry and lambda n in the last entry. And this clearly is a diagonal matrix with the diagonal entries lambda 1, lambda 2, etc. up to lambda n. And this completes our proof. We stated earlier that this is a sufficient condition but not necessary. Let us understand this using some examples. As a first example, consider the linear operator on V defined as L of V is equal to V for all V in V. Notice that the only eigenvalue of L is 1. Therefore, it does not have n distinct eigenvalues. However, if you take any basis of V, then the matrix of the linear map L with respect to the basis BV is equal to the identity matrix. And identity matrix is clearly diagonal. So this operator L is diagonalizable. However, it does not have n distinct eigenvalues. Let us now look at a slightly more complicated example. Let V1, V2, V3, V4 be a basis of a vector space V. And then consider the linear map L from V to V given by L of V1 is equal to 2 times V1, L of V2 is equal to 2 times V2, L of V3 is equal to 3 times V3, and L of V4 is equal to 4 times V4. Now notice that the matrix of this linear transformation with respect to the basis V1, V2, V3, V4 is equal to 2 0 0 0, 0 2 0 0, 0 0 3 0, 0 0 0 4, which is a diagonal matrix. Thus, this linear operator is diagonalizable. However, it does not have 4 distinct eigenvalues. It only has 3 distinct eigenvalues, namely 2, 3 and 4. However, even in this case, notice that we could find a basis of V such that all the elements in the basis are eigenvectors of L. In general, whenever we can do this, we will be able to diagonalize the linear operator. More precisely, we have the following theorem. Let V be a vector space over R or C and L from V to V an operator. L is diagonalizable if and only if there exists a basis of V such that each element in the basis is an eigenvector. I will briefly sketch the proof, and completing the proof will be left as an exercise. First, we will see the sketch of the proof of this direction. So if L is diagonalizable, then there exists a basis V1, V2, etc. up to Vn such that the matrix of L with respect to the basis V1, V2, V3, etc. up to Vn is a diagonal matrix. Let's say the diagonal matrix is lambda 1, 0, 0, 0, 0, 0, lambda 2, 0, etc. and so on up to 0, 0, 0, and the last entry is lambda n. Then notice that L of V1 is equal to lambda 1 V1, L of V2 is equal to lambda 2 V2, and so on up to L of Vn is equal to lambda n Vn. Therefore, the basis V1 to Vn is a basis such that every element is an eigenvector. And this completes the proof of one direction. Now let us see the proof of the other direction. If suppose there exists a basis V1, V2, V3, etc. up to Vn of V such that Vi is an eigenvalue, say L of Vi is equal to lambda I Vi. Then we can show that the matrix representation of L with respect to the basis V1, V2, etc. up to Vn is the diagonal matrix lambda 1, 0, 0, 0, 0, lambda 2, etc. and finally 0, 0, 0, 0, lambda. And thus we have the other side as well. This completes the proof of the theorem. Now notice that this theorem characterizes diagonalizable operators. Why? Because it gives an if and only if condition. However, this characterization is not so useful because in general it is very difficult to verify if there exists a basis V1, V2, etc. up to Vn of V such that Vi is an eigenvector. So we just translated one difficult problem into another difficult problem. And thus this characterization is not so useful. Nonetheless, the theorem deepens our understanding of diagonalizable operators, and I hope you have gained some insight into the topic of diagonalizable operators.